Inside this factory, ordinary minerals are trans something extraordinary. Layer by layer, microscopic materials powerful enough to move car electricity, but how are they actually made? The journey begins at the factory gates. Before a single battery cell can be assembled, carefully controlled raw materials arrive from around the world. But nothing enters production blindly. Every material is inspected first, because one microscopic impurity can compromise an entire battery. Once approved, the materials are stored under tightly controlled conditions. From here, they enter a process where precision becomes everything. Now the materials cross the line from storage into production. What looks like simple powder and chemicals is about to become the heart of a battery. First, the cathode material is carefully prepared. Its particles must be controlled with extraordinary precision before they can be part of a working battery. Inside the processing system, the material is homogenized so its composition remains consistent from one batch to the next. Next comes the anode material, commonly based on graphite. Its job will be to provide the opposite side of the battery's lithium-ion pathway.
Before it can become an electrode, the graphite is refined and prepared to meet the exact physical requirements of the battery design.
Another ingredient plays a quieter role, the binder. It helps hold the active electrode particles together during the battery's long working life.
Even a tiny amount of conductive additive matters. It helps electrons move through the electrode, connecting microscopic particles into an efficient electrical network. Now every ingredient is measured against a precise recipe. Too much or too little can change the performance of the finished cell.
With the recipe verified, the ingredients finally come together. The next step is form these separates form materials into one perfectly electrode mixture.
Inside the high shear mixer, powders, binder, and conductive material are blended into a smooth slurry. This seemingly simple mixture is about to become an electrode. But before this mixture can coat in an electrode, it must pass another test. Its consistency and composition have to be exactly right.
With the slurry approved, it moves through sealed pipes toward one of the most precise stages in the entire factory's, the electrode coating line.
First, an incredibly thin sheet of copper begins its journey through the coating line. This metal will collect electrical current from the finished anode. On the cathode, aluminum performs the same critical job, providing a lightweight current collector beneath the active battery material. Before coating, the metal surface must be exceptionally clean. Even tiny contamination can interfere with the bond between the electrode and its current collector. Now the cathode slurry meets the aluminum foil. A precision coating head spreads an incredibly uniform layer, thin enough to control, yet dense enough to store energy.
The coating moves any further, cameras and sensors inspect for defects. At this scale, uniformity is everything. Once approved, the wet electrode enters a long drying oven, where controlled heat removes the lid solvent and leaves the active material firmly attached to foil.
A graphite-based scission is applied to be slid onto copper, creating the essential electrode. Again, the coating is inspected before it can continue. A defect here could eventually become a weakness inside the finished cell.
After coating, the anode enters its own drying system. Controlled heat removes the remaining solvent without damaging the delicate electrode layer.
Inside the oven, temperature and airflow are carefully balanced. The goal is simple: remove the solvent while preserving the exact structure of the electrode. Now the anode is dry and firmly bonded to its copper collector. Two critical electrodes have finally been created. But the coating is still too thick. Massive precision rollers compress it to an exact density, controlling how much active material occupies every millimeter.
The anode undergoes the same precision treatment. Its thickness and density are adjusted so the finished cell can balance energy, power, and durability.
Now sensors measure the electrode without touching it. Thickness, density, and surface uniformly as the material moves. Then the edges are examined for microscopic defects. A tiny irregularity here could become a serious weakness once the electrode is sealed inside a cell.
Once the electrode passes its inspection, it's wide sheeted into narrow strips. Each strip is destined to become part of an individual battery cell. Now the enormous sheet has become multiple precisely sized electrode strips, each prepared for the next transformation.
These narrow strips are now wound onto individual reels. The electrodes are ready, but the most delicate part of the battery is still ahead. Between the two electrodes sits one of the battery's most important layers, the separator. It's incredibly thin, yet it must keep the electrodes apart. Because even a microscopic defect could compromise the cell, the separator is inspected with extraordinary precision before assembly begins. electrodes converge. Anode, cathode, and component separator in machine designed to align them down to microscope tolerance. Then the transformation begins. The three layers spiral together, creating the tightly packed structure that will eventually live inside the battery. That spiral is called a jelly roll. Hidden inside it are the electrodes and separator layers that will drive the battery's entire electrochemical reaction. Meanwhile, the empty metal casings are prepared. Each one is precisely positioned to receive the delicate electrode core. Now the jelly roll enters its metal home. The fit is deliberately precise because there is very little room for error inside a finished cell. Next, the electrode tabs are connected to the cell's terminals. A tiny weld creates the electrical pathway that will eventually carry current outside the battery. Before the cell goes any further, those connections are tested. If something is wrong now, the factory catches it before the chemistry ever goes inside. With the cell structure assembled, another critical ingredient is prepared, the electrolyte, the medium that allows lithium ions to move between the electrodes.
First, the solvent is purified to an extremely high standard. In battery manufacturing, even microscopic contamination affect performance and reliability. Precisely measured components are then combined to create the electrolyte formulation. Its chemistry must be carefully balanced for the battery to function safely and efficiently.
Before it reaches the cells, the finished electrolyte passes through a final filtration stage, removing unwanted particles before the most delicate step begins. The partially assembled cells now enter a controlled filling chamber. Every cells must receive the right amount of electrolyte without introducing contamination. Now the electrolyte enters the cells. Tiny quantities are measured with extraordinary precision because the chemistry inside must be carefully controlled.
But filling is not enough. Vacuum and pressure are carefully controlled to help the electrolyte deep into the porous electrodes and separator.
Then the cells rest. The electrolyte is given time to fully wet the internal materials, reaching areas that cannot be seen from the outside. Once the electrolyte has penetrated the cell, the housing is permanently sealed. The battery is now physically complete, but it still isn't ready to use. Now comes a crucial transition. These seals enter formation, where controlled electrical cycles will activate the chemistry inside and reveal whether the manufacturing process succeeded. Each sealed cell now enters a formation rack, where individual electrical connections prepare it for the process that will activate its chemistry. Then the first controlled charge begins. Slowly and precisely, electrical energy activates the chemistry that will make each cell capable of storing power. But the factory doesn't simply charge them and stop. The cells are deliberately discharged and cycled, teaching the chemistry how to behave under real electrical conditions. Behind the racks, engineers watch thousands of measurements in real time, voltage, current, and temperature, searching for anything that doesn't behave exactly as expected.
Temperature is watched just as closely. A properly controlled cell should behave predictably, and the factory is constantly looking for signs that something is wrong.
After repeated controlled cycles, formation is complete. The chemistry has been activated, but the factory still has to prove that each cell can perform consistently. Next, the cells are allowed to rest under controlled conditions. This aging period gives engineers another opportunity to chemistry stabilizes over time.
Once the cells have stabilized, their voltage is checked individually. This simple measurement can reveal whether the electrochemical process as expected. Next comes one of the most important tests, capacity. Each cell is measured to determine how much energy it can actually store and deliver.
Internal resistance is measured next. It helps reveal how efficiently each cell can move electrical energy and whether its performance falls within the factory's strict limits. After testing, every cell receives a performance grade. Capacity, voltage, and resistance data are to strict factory limits. Cells with similar characteristics are then grouped together. Matching them helps ensure consistent performance when many cells work side by side. Each approved cell is given a microscopic identification mark. That code allows the factory to trace the cell through production and quality control.
Then the outside of every cell is examined. Cameras search for human arms for defects that human eyes could easily miss.
Even the physical dimensions are checked. Diameter, height, and terminal position must stay within extremely tight manufacturing tolerances. One final electrical check remains. The factory verifies that each cell still meets its required electrical specifications after the entire manufacturing journey. Only cells that meet every requirement move forward. Anything outside the limits is automatically separated instead of being allowed into the final product. After passing inspection, the approved cells finally enter packaging. From here, the factory's focus shifts from manufacturing to protection and transport.
Each cell is separated inside of a protective tray, preventing unwanteds of batteries travel through the supply chain.
After months of precision manufacturing, testing, and inspection, the cells are finally packed. They are ready to leave the factory and become part of the technology that powers modern life. Every shipment is secured for the journey ahead. Thousands of individual cells can now leave the factory as precisely protected industrial cargo. From this enormous factory, the finished cells begin their next journey toward the machines, vehicles, and devices that will eventually bring them to life. These small cylinders may look simple, but together they can power electric vehicles, portable electronics, and entire energy systems. Inside this small cylinder is an extraordinary amount of engineering, materials, chemistry, precision manufacturing, and thousands of quality checks. From raw materials to a finished cell, every step controlled with extraordinary precision. And that is how a battery to hold in your hand becomes powerful enough to help drive the future.